This is part 2 of my discussion on hybridization. The part 1 is actually more of an introductory portion that's more general chemistry than organic, and in fact, the irony is that there's really no discussion on hybridization in the previous part. This is the discussion that will include that. But what we should know so far are basic principles like we now know, we have now reviewed that there are two types of overlaps, the stronger sigma 1 and the weaker pi overlap. And the sigma bond is usually present in single bonds, whereas pi bonds are secondary to sigma bonds, such that if I have, for example, a single bond, the single bond is automatically a sigma 1. If I have a double bond, then that is two bonds. One is a sigma and the other one is a pi. And then for triple bond, there's only one sigma and there are two pi bonds. And as you see, there's always only one sigma because the sigma is the first bond only. Such that if we now look at a carbon with complete set of bonds, 4, remember, for carbon, if I have a carbon that is particularly an alkane, that is, all my bonds are single, then every bond there is automatically sigma. That means for a carbon in an alkane, that is 4 sigma bonds, no pi bond of course. If I have a carbon that is part of a double bond, let's say it's an alkene, then this one is sigma, this is sigma, and the double bond is sigma and pi. So that means for a carbon with a double bond, that is usually 3 sigma, 1 pi. And for a carbon in an alkyne, which has a triple bond, this one is sigma, and then in the triple bond, there's only one sigma, and the rest of the two are pi bonds. So for a triple bonded carbon, that is 2 sigma, 2 pi bonds. And this is the mystery I was talking about when I ended my previous part or discussion. How is it possible that carbon, as in carbon with 6 valence electrons, carbon with this excited state. How is it possible that carbon can have three different sets of bonds wherein the sigma and the pi bonds vary? In fact, that is very odd because now if I go back to my excited state for carbon and if we try to analyze what type of overlaps are present, you would be surprised. Remember, a sigma bond is usually for s orbitals, and a pi bond is usually for p orbitals. That means that this one is going to be equivalent to 1 sigma, and then these 3 p orbitals are going to be equivalent to 3 pi. This makes matters even more confusing. Like, do you even see any of our 3 combinations here? A combination that matches the one that we have here? The answer is no. And that's like a whole ton of confusion for us because, before we knew about sigma and pi, we were already very happy that by showing the excited state, we already have 4 bonds and period. Like, why make it complicated? And we have to make it a little more complicated because, as you will see in reactions, the fact that sigma is strong and pi is weak will affect a whole lot of different factors in how organic compounds react or change. So let's answer this question. How is it possible that carbon is like a shape-shifting atom that it can, at will, or depending on the case, have 4 sigma, sometimes 3, sometimes 2? The answer is a word called, well, that's the title, hybridization. First, before we try to give the details of this one, we have to, define what a hybrid is. And the good thing, it's not really a complicated word. When you say a hybrid, usually other synonyms that come to mind are mixture or crossbreed or merging, or I'm actually losing words, but the fact that hybrid means a mixture of two or even more different things will already be noticeable as I discuss it detail per detail. So, the idea here is that in hybridization, we're trying to mix different proportions of s orbitals in p orbitals in order to get a, let's say, mixed breed or crossbreed of an s in the p orbital. That, SPX, we can call it like that. That crossbreed of an s in a p orbital is called a hybridized orbital. So we call this a hybridized orbital. And in perspective, when you see our orbitals being solo orbitals, like it's S only or P only, you call such orbitals as unhybridized, simply because they haven't been mixed yet. And the ratio of hybridized to unhybridized orbitals will give us the different proportions of sigma and pi bonds that we see. Now, let's get straight to it. Let's say, first situation, I'll just choose a simple color. Let's go back to the old one. Let's say I have a possibility that I mix all of these orbitals, meaning 1s and all 3p orbitals. Of course, when we try to consider the conservation of energy law, then that means if I mix 4 orbitals, then I must end up with 4 orbitals as well. So meaning I have 1, 2, 3, 4. And these orbitals are now what we call hybridized because they are mixed together. Now the problem is, what's the name of this? You just borrow it from what you mixed. What did you mix anyway? 1s, 3 p orbitals. So the name of these 4 orbitals are sp3 hybridized orbitals. And they also have 1 electron each. So now, just like the original one, I know that I have 4 unpaired orbitals willing to make 4 bonds. But now what's the catch? Remember something that I told you a while ago, or even in the previous part, that if it's SPX, it's sigma bonding? Yeah, right? I didn't even call this in part 1 as a hybridized orbital. But now what I'm trying to say is, um, let's skip the details because it's more of quantum or inorganic chemistry to discuss why. But let's just remember that every hybridized orbital has a higher tendency to form sigma bonds. Now, let's go back to sp3. Since all of these are hybridized orbitals, that means that all of this will form sigma, 4 of them. Such that if I have a carbon, which I just showed you a while ago, this one, I have a carbon with 4 possible sigma bonds. Then, therefore, I can say, how is it possible that this carbon can form 4 bonds that are single? Then that can be answered by, I can say, my carbon here is sp3 hybridized, or my carbon here has an sp3 hybridization. Okay. Oh, and by the way, every time we have an sp3 hybridized carbon, it has a particular geometry. The geometry of all sp3 carbons are more or less tetrahedral, and they have a specific bond angle of 109.5 degrees. That means that if we're going to be realistic about the exact shape of an sp3 carbon's bonds, they form these angles. Like this one is 109.5, the other angle is 109.5, and so on. Now, let me just clarify, we don't really draw carbon like this if it's sp3. It's more like a pyramid. So like if this is my carbon and has an sp3 hybridization, it more looks like a pyramid or a tripod. Okay? We'll get to that when we discuss other topics like isomers. But for now, we have to realize that not all the time my carbon will be sp3 hybridized because not all the time my carbon has 4 sigma bonds. Okay? Like for example, let's switch a color. What if I have now a carbon wherein, just like what I said a while ago, has 1, 2, 3 sigma bonds, but now with 1 pi bond? Definitely, you cannot use the sp3 hybridization for that because in the first place, there's no pi bond even in sp3. It must be a different way of mixing or hybridizing, I don't know if there's such a word, the orbitals here. So maybe what we can do is, okay, why not mix just one s, and instead of all 3p's, just 2 of them. And then the other one is remaining, will be, unhybridized. It will remain unhybridized. So since I'm gonna mix only these 3 orbitals, then I'm gonna end up with 3 hybridized orbitals only. And since I only mixed 1s and 2p orbitals together, the name of each orbital here is sp2. Of course, we conserve the electrons as well. And remember that we didn't mix this, so it will stay like that. It will stay unhybridized. So now, what type of bonds or overlaps would there be? Well, I have 3 hybridized orbitals, and take note, it doesn't actually matter if I am sp3 or sp2. The fact that it's hybridized, just like what I said a while ago, they will form sigma bonds. So there are three of them. We have three sigma bonds. How about this unhybridized p orbital? Well, remember, what does a p orbital most likely form? Well, it forms usually a pi bond, right? So that means that this unhybridized p orbital will give us one pi bond. Oh, look, these three represent these three, and this one pi bond is this single one. In other words, that means that my carbon here with a double bond is said to have an sp2 hybridization. With this mixture of orbitals, 3 hybridized, 1 unhybridized. And of course, if this is a different way of bonding, then you expect that the shape of this is different also. The shape of sp2 or the geometry of sp2 atoms instead of tetrahedral is trigonal planar, and the bond angles are 120 degrees. Okay, and planar means that an sp2 carbon is flat, and I'm saying that because there's something significant about the flatness or the two-dimensionality of sp2 carbons, as we will cover in the next topics. And then finally, what if I have the choice to combine one s and only one p orbital, leaving the two other p orbitals unhybridized? If we do that, we end up with only two hybridized orbitals, one s and one p, so therefore the name is sp. Well, you may say sp1, but since there's only one p orbital there, then we just call it plainly as sp. And then the remaining two orbitals, py and pz, stay unhybridized. And now hopefully you're seeing the pattern here, because now it's kind of obvious the fact that these are two hybridized orbitals that will give us two sigma orbitals or sigma overlaps. And then for the p orbitals here that are unhybridized, that will give us two pi bonds, which is perfect for conditions like this. Remember, a triple bond has 2 sigma and 2 pi, which is just like this. So that means I can say that the carbon with a triple bond has an sp hybridization. And in this case, the shape of this one is more of linear with bond angles of 180 degrees, which makes sense because a line has 180 degrees, right? But it's not always just a triple bond which can have an sp hybridization. What if I have a carbon with two double bonds? Let's remember the fact that every double bond is composed of one sigma, one pi, right? And what if I have two? Then I have another sigma and another pi. So what combination does that give us for this carbon? Well, 2 sigma and 2 pi. That means that this one is also sp hybridized. And I'm saying this because it's kind of a warning for some people who try to make an immediate shortcut na, alright, if I have a single bond, then it's all sp3. Or if I have a double bond, it's all sp2. That's not always like that. Now, if you have a double bond, you have to be careful. Ask first, does the carbon have one double bond or two double bonds? Because that would be different. If a carbon has one double bond only, right, that's sp2. But the moment I have a carbon with two double bonds, or two pi bonds that is, then I have sp2. Hopefully that clears this up, and in order to end our discussion, I want to give you this exercise. I want you to pause this one and try to answer all of the following encircled atoms. For every encircled atom, please designate their hybridization. Is it sp3, sp2, or sp? Actually, if you try to do it, you may end up with some questions that I will try to answer. So pause it now. Or if you don't want to answer this, then I can answer it now. Well, let me give you the solution for this. So let's do it one by one. First, this carbon has a triple bond, and it is clear that if I have a triple bond, it will have the hybridization of sp. This carbon, oh, by the way, this is a carbon. Now, what you want to notice here is that we have a weird structure, right? Like you may be asking, why is it drawn like that? That is because, okay, That is because, first, let's answer this. This also has a triple bond, right? So definitely it's sp. If I ask you, what again is the hybridization of sp? I mean, what is the geometry of sp? Linear, right? And if it's linear, then that means that any bond next to sp atoms must follow a straight line. So that's something that you may find amusing because this is really a weird structure at first, but you have to get used to it. Next, how about this one? There's no double bond, there's no triple bond, so this one is sp3. So what you can use as a shortcut is, if you don't see any multiple bond, you don't see a double, you don't see a triple bond in that carbon or that atom, sp3. How about this? Oh, you have to be careful because in this atom, you have this double bond, right? So since it has one double bond, then this is sp2. Also this one, since this double bond belongs to this carbon, then this is also sp2. This carbon also has a double bond, so this is sp2. Now this is interesting. If you already paused the discussion and I tried to answer them one by one, you may have realized why is it I encircled the oxygen. And that is because you have to take note that hybridization does not only apply for carbon but also to oxygen, nitrogen, and similar atoms. Okay? But primarily carbon, nitrogen, and oxygen. Now, since oxygen here has a double bond, it is sp2, meaning that we will treat oxygen and nitrogen the same way we treat carbon. That if I have a double bond for oxygen, it's sp2. If I have a triple bond for nitrogen, it is sp, and so on. Okay, let's go back here. Well, I don't see any double or triple bond, so this carbon is definitely sp3. This oxygen right here doesn't have a double bond, so like carbon, if it doesn't have a double bond or a triple bond, it's also sp3. This nitrogen, I don't see a double or a triple bond, so this is also sp3. This carbon has a double bond, so it is sp2. And this carbon, now you have to be careful. Take note that this carbon has not just one, but two double bonds, so this is sp. Now, before I end, some of you may come up with a question. All right, so it's sp. So shouldn't we draw this in a straight line? Yeah, that's right. I actually intentionally made this incorrect because that allows me to tell you, get used to the fact that if I have two double bonds, you have to draw it straight because the carbon in the middle has sp2 and the shape should really be linear. So yeah, it should actually be drawn like this instead of like this. If you spotted that, then that's good. But this is where I end, and we will apply this hybridization thing to most other next topics.